Okay guys, so to end the week we're going to do the second lesson in Unit 9, which is about irrational numbers. We've talked about irrational numbers in 7th grade, and we've talked about them a little bit in this class, and we're going to go fully into detail now. So back in 7th grade, we had a whole lesson on the number sets. So we talked about how the set of real numbers is separated into rational numbers and irrational numbers. So what we discussed basically in 7th grade was that a rational number is anything that can be written as a fraction, and that included decimals that were either repeating or terminating. So that's still true. A irrational number is any number that's not rational. So anything that you can't write as a fraction is defined as irrational. So the numbers are non-terminating, which means if it's a decimal, so it could be a decimal that never ever ends, such as pi, which we discussed, or non-repeating decimal representations. So let's take a look at exercise 1. Let's consider a number that's rational and one that's irrational, which means not rational, right? Consider the rational number 2/3 and the irrational number the square root of 1/2. Both of these numbers are less than 1. And keep in mind, just because 1/2 is rational does not mean that the square root of 1/2 is not rational. Okay, so first we're going to draw a pictorial representation of 2/3 on the rectangle here. So I'm going to approximately, oh, that's not good, break it up into thirds. Okay, that's still pretty bad. And 2/3 would be shaded in 2 of them. Okay, now using our calculator, we're going to give the decimal representation of the number 2/3. So you guys might remember this. Plug in 2/3, 2/3, and you get 0.6666667. Remember that the 7 at the end is just because your calculator is rounding. Okay, dot, dot, dot. So this is really 0.6 repeating. We've discussed that in 7th grade. Now, write out all of the decimal places that your calculator gives you for the square root of 1/2, and notice it does not have a repeating value. So to do the square root, if you guys don't remember, you do second and the x squared button, second, x squared, and then inside here you put 1/2. I'm going to use my alpha y equals button, 1/2. Okay, and I get this number here. Writing them all out, I get 0.70710678812. You cannot see any evidence of anything repeating here, right? Why could we not draw a pictorial representation of the square root of 1/2 the way that we can for 2/3? Well, if you think about it, with the number 2/3, you can divide the whole into an integer of 3 parts, and then you take the integer number, which is of those parts, which is 2, that would represent the quantity. And that's the whole idea of what a rational number is. When you have an irrational number, there's no way of doing that, right? If this was the square root of a perfect square, I would be able to do it. But I don't know what the square root of 2 is, so there's no way of me doing this. Okay? So irrational numbers are necessary for a variety of reasons, but they are somewhat of a mystery. In essence, they're a number that can never be found by subdividing an integer quantity into a whole number of parts and then taking an integer number of those parts. That's just a really fancy way of saying that we can't do this. We can't take an integer number and break it up into parts. There are many, many types of irrational numbers, but square roots of non-perfect squares are always irrational. So that means if you're taking the square root of a number that's not a perfect square, it's always irrational, no matter what. The proof of this is beyond the scope of this course. And by saying that, I can tell you that was a proof that I had to do in one of my college courses. So it's a little bit much. We don't need to do it here. So for exercise 2, first what we're going to do is we're going to take a look at these in the calculator so that we can prove to ourselves just by looking that they are irrational. So square root of 2 is one of the most famous ones. I know that this is not a perfect square, and that's enough actually to conclude, but let's look at the square root of 2. We get 1.4142135662. Nothing repeating, nothing terminating, and it doesn't count that the calculator gets cut off after those digits. Square root of 10. 10 is not a perfect square, sorry. See that? 3.162277766. You can see that the two numbers seem to be repeating, but that doesn't count as a repeating decimal, so don't get thrown off by that. Square root of 23. Again, 23 is not a perfect square, so I already know. And I get this number here, 4.795831523. Again, no evidence of anything repeating. So to basically summarize the point of that, if your square root is not a perfect square, it's automatically irrational, even when you can simplify it. So rational and irrational numbers often mix, as when we simplify the square root of a non-perfect square. So like I just said, even when you simplify it, it's not going to be rational. You can simplify it so that it has a piece of a rational, but the whole number itself is never going to be rational, okay? So without the calculator, let's figure out between which two consecutive integers this number will lie. We did this when we talked about the co-op. We looked at what two perfect squares is this number in between. It's in between 25 and 36, right? So the square root is going to be in between 5 and 6, right? Using the calculator, we're going to write out the decimals for the square root of 28. So let's see what it is. Now we know it's irrational because 28 is not a perfect square. Let's take a peek at what we get when we do the square root of 28. We get 5.291502622. So as we predicted, it is a number between 5 and 6. And now we're going to write this in simplest radical form, which is what we did the past 2 days. So we try to think of what's the largest perfect square we can divide 28 by. Remember to always check in your calculator to make sure, but it is going to be 4 times 7 here. So I break this up into the square root of 4 times the square root of 7, which gives me 2 radical 7. This number itself is not rational. It's still irrational, okay? So now we're going to write the decimal representation for this. Plug that into your calculator and see what happens. 2, and you don't even have to do anything. You just do radical 7 like that. Interesting. Same exact thing. And that's because they are the same exact thing. Just like when you simplify something in algebra, it's equivalent to the original. When you simplify radical, it's equivalent to the original also. Okay, so it's still irrational, even though you simplified it. Very important to note that. Okay, so it appears that a non-zero rational number times an irrational number still results in an irrational number, right? So even though we're multiplying radical 7 by a rational number, which is 2, we still get the irrational number. So we should also investigate what happens when we add rational numbers to irrational numbers. So we're going to see what happens when we do this. We're going to use the calculator, okay? Do 1/2 plus the radical 2, so use your alpha y equals to do 1/2, okay, plus radical 2, and see what we get. 1.914, blah, 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 it's clearly irrational. 1.914213562. So this is irrational. Okay? If you think about it, if you already have a number that's going on forever, if you multiply it by a rational number, it's not going to make it rational. It's just going to make it even larger. Same thing when you add. If you add a rational number to an irrational number, it's already going on forever. Now you're adding more onto it, so it's still going to go on forever. So it stays irrational. Okay, let's check 4/3 plus the square root of 10. Again, you can use alpha y equals to get your fraction button. 4/3 plus square root of 10. And again, another irrational number, 4.495610994. That's irrational. Okay. And we'll finish off by subtracting 7 minus the square root of 8. So we've got 7 minus the square root of 8. And same thing, it's still irrational. 4.1715,728,75. Okay, so to conclude, we're going to fill in the statement here. When a rational number is added to an irrational number, the result always stays irrational. So regardless of whether you're multiplying by an irrational number or adding or subtracting, it still stays irrational. Okay? So for the final exercise, we're going to decide which of the following is irrational. And if you need to, you can use your calculator to see if the decimal doesn't repeat. And don't be fooled by the square roots. Okay, so let's take a peek here. Hopefully you can see already. The square root of 25, that's a perfect square, so I automatically know it's rational because that's equal to 5. 7/2 is written as a fraction. It's already written as a fraction, so it's obviously rational. So let's just write rational. This is rational because it's written as a fraction. Then this is 4 minus the square root of 9. Just because you see a square root sign doesn't mean it's irrational. I know that the square root of 9 is 3. 4 minus 3 is 1. That's rational. And finally, we got this guy, 3 plus the square root of 6. This is an irrational number, and I know that because 6 is not a perfect square. So I already have an irrational number. If I add something to it, it's going to stay irrational. So the whole thing is irrational. And of course, if you plug it into your calculator, you can see that 3 plus the square root of 6, oops, I didn't need that, is equal to 5.449489743. No evidence of repeating. So that's your answer. Okay, guys, have fun with your irrational numbers.